Now that we know what a normal subgroup of a group is, we need to make good on that promise that normal subgroups are going to allow us to treat their cosets as though they were elements of the group, so that we can do arithmetic with the cosets of a normal subgroup just by doing arithmetic with the elements of the group that represent those cosets. Let's take a look at how that works. What we're really talking about is a construction called a quotient group. And the definition of a quotient group is if G is a group and N is a normal subgroup of G, the elements of the quotient group are exactly the cosets of N in G, and the operation that turns this set of cosets into a group is that if I multiply the coset Gn by the coset Hn, then the result is the coset GH times N. And perhaps you can see just in that very equation where the numerality assumption comes in. So a quotient group, we're going to treat the cosets of N as though they're the elements. So as a quick example, let's look at Z mod 12 again with the subgroup 0, 3, 6, and 9. Call that H. The cosets are 1 plus H and 2 plus H, as you can see here respectively. And we showed already that this was in fact a normal subgroup. Actually, since Z mod 12 is abelian and H is a subgroup, we know for sure that H is a normal subgroup. So what does a quotient of Z mod 12 by H look like? Well, it takes each one of these cosets and it treats it like it's its own element. So there are actually 3 elements in Z mod 12 quotiented out by H. The elements are H itself, 1 plus H, and 2 plus H, the 3 cosets. And if we want to do arithmetic with these cosets, let's just take a look at what we get when we add 1 plus H to itself. What does that mean? It means I'm going to take all of the elements in 1 plus H, namely 1, 4, 7, and 10, and add them to all of the other elements in 1 plus H. So what I get is actually a total of 16 different sums, 1 plus 1, 1 plus 4, all the way up to 10 plus 10. But modulo 12, you can check this, all of those sums take on just the 4 different values, 2, 5, 8, and 11. And what is that but the coset 2 plus H? How could we have known that from the outset? Well, again, when you do arithmetic with cosets, you do it using the elements that represent those cosets. So 1 plus H added to 1 plus H had better be 2 plus H because 1 added to 1 is 2. Here's some more examples. So going back to Z mod 12 again and taking this time the normal subgroup that has 6 elements, 0, 2, 4, 6, 8, and 10. What are the cosets? Well, there's really only one that's not N itself, and that's 1, 3, 5, 7, 9, and 11, 1 plus N. And so the quotient group has those 2 elements, N and 1 plus N. Now what does the arithmetic look like? Let's make up a quick multiplication table, if you will, and it's really an addition table in this example, for these 2 cosets. Well, what are the N's? N is really just the even integers in Z mod 12, and 1 plus N are the odds. And if I add evens to evens, I get evens. If I add odds to odds, I get evens. And if I add evens to odds, I get odds. Well, that multiplication table there is exactly the multiplication table that defines the cyclic group of order 2, Z mod 2. So in fact, G mod N is isomorphic to Z mod 2. Just by writing out the multiplication table. We're going to see in a little while a way to characterize the arithmetic of a quotient group in a little bit smarter way, but we need a little bit more terminology and tool work before we can do that. In the meantime, we're just going to make some observations like the one we just made. In fact, because the cyclic groups are all abelian, that means that any of their subgroups are normal subgroups, and if P divides Q, in other words, if Q is a multiple of P, then we can show that Z mod Q, quotiented out by Z mod P, is really just Z mod Q divided by P. This may be where the quotient group language comes from in the first place. So in this example, what we really had was Z mod 12 quotiented out by H, which is isomorphic to Z mod 6. And their quotient was isomorphic to Z mod 12 divided by 6, which is 2. All right, let's get to a non-abelian example, because this is always where the fun stuff happens. We saw this example of a normal subgroup in the previous video, consisting of these 3 2 plus 2 cycles along with the identity. So what does the quotient group of G with respect to this normal subgroup look like? Well, let's again start by listing all of the cosets. This takes a long time, because we have 24 elements of S4 to account for. But it turns out that when we list all of the cosets, there are 6 distinct versions of them, having the elements listed here. And when we go to make the quotient group G mod N, each one of these cosets is going to be one of the elements in that group. So all told, G mod N is going to be a group that has 6 elements. Well, that's all fine and dandy, but not every group that has 6 elements is created equal. So which particular group of order 6 is this? Is it the cyclic group of order 6? Is it maybe the cross product of Z2 with Z3? Or is it the symmetric group on 3 symbols, S3? That's also a group of 6 elements. Well, to figure out which it is, all we have to do is observe that this quotient group is not going to be an abelian group. Why not? Well, just to compare, for instance, the result of 1, 2 and 1, 3 in one order and then the opposite order. Just by simplifying this product of cycles, we find out that indeed those two products do not give us the same thing. So since G mod n is not abelian, it can't be isomorphic to either of these Z mod 6 or Z2 cross Z3 because those are abelian. Therefore, since these are the only 3 groups of order 6 up to isomorphism, G mod n had better be isomorphic to S3. So where we need to go with this next is to think about how quotients relate to normal subgroups and how they also relate to homomorphisms, all of this terminology that we had a couple of videos ago. And one of the most important players here is something called the quotient mapping theorem, that just says that whenever we have a quotient group, there's also homomorphism from G to that quotient group that's onto, so it's an epimorphism. And the reason that this exists is, again, because the arithmetic that we do with cosets is exactly the arithmetic of the elements that are used to represent those cosets. What this does is it establishes a one-to-one correspondence between normal subgroups of G and homomorphisms whose domain is G. And this correspondence is exactly set up, according to the quotient mapping theorem, by the operation of taking the kernel. In other words, what this is saying is that every normal subgroup of G is the kernel of some homomorphism out of G. And conversely, every homomorphism out of G, its kernel is a normal subgroup of G. So as a quick example, here's this even subgroup of Z mod 12 again. Which homomorphism out of Z mod 12 has this as its kernel? Well, what we need to do is send each of these 6 elements to the identity in this group being 0. Well, one way to do that is just by multiplying each one of them by 6. What happens to the other elements, 1, 3, 5, 7, and 11? The other coset, well, it turns out all of those, when we multiply them by 6, give me something that's congruent to 6 mod 12. So the kernel of this homomorphism is exactly H, actually that should say N, the normal subgroup 0, 2, 4, 6, 8, 10 itself. Meanwhile, the image of this homomorphism consists of just 0 and 6. 0 is where all of the elements in N are going, and all the elements in the coset 1 plus N are going to 6. Here's another example, again, made more interesting by the use of a non-abelian group. Let's think of the dihedral group with a square again, and define an endomorphism, in other words, a homomorphism from D4 to itself, that sends the rotation R to the identity element, and the transposition T is just sent to itself. The reflection T is sent to itself. So this defines the following endomorphism of D4 that sends these 8 elements to those 8 elements. Notice all the rotations, regardless of how many times they're rotating, they're all getting sent to the identity. And all of the reflections are getting sent to the same reflection T. So this is what the endomorphism actually looks like. Now what's the kernel of this homomorphism? Well, the kernel is everything that's getting sent to the identity. And so it's all the elements, ER, R squared, and R cubed. All the rotations are the kernel of this homomorphism. And so that implies that the subset of rotations is a normal subgroup of D4. Now what's the quotient? The quotient is going to be the group that consists of just these 2 cosets. And because there's only 2 of them, we know for sure that that quotient is isomorphic to Z mod 2. Finally, before we move on, we wanted to get to this place where we know how to characterize what the quotient of a group by one of its normal subgroups looks like. And the big tool there is called the first isomorphism theorem. The first isomorphism theorem has 2 components that are not that surprising. Namely, one of them that we've already showed, that K, the kernel of any homomorphism out of G, is a normal subgroup of G. And also that the image of a homomorphism is a subgroup of its codomain, in this case, the group H. So these first 2 are not news. What's interesting is that the image is actually isomorphic to the quotient of G by its own kernel, by the kernel of the homomorphism phi. So what this does is it's going to give us a very convenient way, a quick and dirty way to characterize the quotient of G by a normal subgroup N. All we have to do is say, well, if we know what N is as the kernel of a homomorphism, so for instance, if N is 0, 2, 4, 6, 8, and 10, like on the previous slide, that was the kernel of the multiplication by 6 map, then when we take that quotient, it's going to be isomorphic to the image of that same homomorphism But remember, we showed the image of that homomorphism had just 0 and 6 in it. And with addition modulo 12, that's isomorphic to Z mod 2. So related to the first isomorphism theorem also is the fourth isomorphism theorem that we're going to use a bit later. And that shows us that there's a relationship between the subgroups of a quotient and subgroups of the original group. And it goes like this. To every subgroup of G that also contains N, we can associate a subgroup of the quotient group G mod N. What does it look like? Let's again look by way of example. So Z mod 16 is our group, and 0, 4, 8, and 12 is our normal subgroup. Well, we can think of that as being the kernel of the multiplication by 4 map, and therefore the quotient G mod N is isomorphic to the image of that homomorphism by the first isomorphism theorem, and the image of the multiplication by 4 map in Z mod 16 is also 0, 4, 8, and 12. Now let's take a subgroup of G mod N. So 0 and 8 form a subgroup over here on the right. So how do we associate to that some subgroup of the original group? Well, let's just take the inverse image under this phi of our elements in the subgroup. So the inverse image of 0 is everything which, when we multiplied by 4, gave me 0 mod 16. 0, 4, 8, and 12, namely. But then the inverse image of 8 is everything that turns into 8 when we multiply by 4, which consists of 2, 6, 10, and 14. So notice on the left here, what I have is actually a subgroup, 0, 2, 4, 6, 8, 10, 12, 14, and that subgroup contains N, 0, 4, 8, 12. So there's a one-to-one correspondence between subgroups of G that contain N and subgroups in the quotient G mod